Okay, so today we're going to be looking at chapter 33, which is the nature and propagation of light. So we're going to be studying how light is reflected, refracted, and basically just how it behaves differently as it travels through different mediums compared to a vacuum. So the first thing we want to talk about is the fact that light is both a particle and a wave. So I'm sure a lot of you have heard that that all particles are both particles and waves, and this is true obviously for photons as well. So a light particle is called a photon. Sometimes you might see it represented by the Greek letter gamma. So they're called photons. Photons are massless and they travel at the speed of light. So any particle that's massless can travel at the speed of light. Anything else cannot travel at the speed of light. So electrons, protons, neutrons, they all have mass, so they cannot travel at the speed of light, while photons can. Now, obviously, photons, since they are light, will be traveling at the speed of light, but any massless particle can also travel at the speed of light as well. So photons are also the force carriers for the electromagnetic force. Now we talked about this a little bit at the beginning of 7D when we talked about the different forces of nature. So whenever we have an electromagnetic interaction, whether we have two electrons that are repelling each other, two magnets, the north and south pole that are attracting each other, any kind of electromagnetic interaction, that interaction is mediated by photons, by the force carrier of the electromagnetic force. So not only are photons light, when we look at the sun, we're seeing a stream of photons coming at us, but they also are what mediate the electromagnetic force. And all of this is described by what we call quantum electrodynamics. So once you get into like the quantum nature of interactions and particles, we use quantum electrodynamics compared to classical electrodynamics, which you saw in 7D. So quantum electrodynamics is basically what we have when we take Maxwell's equations, which treat light purely as, or electromagnetism purely as a wave, and then sort of introduce these particles to it and say, well, what happens if it's really mediated by particles instead of just a pure wave? We get what's called QED. So obviously we're not going to be studying QED, but I just figured I'd throw that out there so you guys know if you see it. So light was initially believed to be a particle. So like back, in the ancient Greek philosophers, they thought that light was a particle. Then as things progressed a little bit, like in Newton's time, he thought that light was a wave. And then we eventually realized that light is both a particle and a wave. So two very famous experiments sort of describe this dual nature of light. We have the photoelectric effect, which Einstein explained and won him the Nobel Prize. He actually didn't win the Nobel Prize for relativity. He won the Nobel Prize for the photoelectric effect. And then we have what's called Young's double slit experiment. So for the photoelectric effect, physicists had found that if you shine a light on a metal, it will eject electrons of a certain energy. So you shine some kind of light on it, and you can measure the energy of the electrons that are ejected. Because remember, in a metal, the electrons are essentially free to move around. So it will eject these electrons at some energy. So what they found was that if you shined a light of very low intensity and low energy, so low energy would be long wavelength, it ejected one energy of electrons. And if you shined that same wavelength of light, so the same energy level of light, but just more intensely, so essentially just more like bright, it didn't change the energy of the ejected electrons. Now, if you're thinking of light as a wave, this wouldn't make sense because you'd expect as you shine more and more light on it for the energy of the electrons to increase. But this didn't happen. It just increased the number of electrons that was being ejected, not their energy. And the only way you could get the energy of the electrons to increase was by shining a higher frequency or a more energetic light at the metal. So if you shone something that was very high energy, like an X-ray, at the metal, then you could get a higher energy electron being ejected here. So the energy of the electron being ejected was not dependent on the intensity. It was only dependent on the frequency or the energy of the light coming in. This light here. So that suggested to Einstein that light was actually made up of particles, not just waves. So he explained this. He was able to successfully explain the photoelectric effect, and he got the Nobel Prize for that. Then we had Thomas Young, who I think we will talk more carefully about this experiment when we do diffraction. So he basically came up with an experiment. He shot two lights, two beams of light through two slits and showed that they interfere like waves would. So now we have these two experiments that basically show that light is both a particle and a wave. So the big takeaway from this is that in different scenarios, it's more convenient to think of light as a wave, and then in other scenarios, it's more convenient to think of light as a particle. So when we're talking about emission and absorption, anything that has to do with emitting light, radiation, anything like that that's emitting or absorbing light, it's better to think of it as a particle. If we're talking about light propagating, so what we're going to be doing today, we're looking at light propagating through a medium, then it's better to think of it as a wave. So it depends on what kind of situation you're looking at that tells you if you should think of the light as a particle or a wave. So since we know now we're going to be looking at light as a wave for this chapter, there's just a couple things we need to some vocab that we need to just get straight. So a wavefront, which we used a little bit in some of our previous chapters, a wavefront is essentially just like pick like a point on the wave and basically just follow that point as it propagates. So here we have like some spherical wavefronts, so we have some point source here that's emitting waves in all three directions. Could be sound waves, could be light waves, whatever. So it's emitting these waves in all three directions, and these are our wavefronts here. And you can just think of it as like, okay, this is the peak amplitude for at each wavelength, each successive wave. This is the peak amplitude, and so these are separated by like one wavelength, sort of like that. And like I said, you could pick any point on the wave. It doesn't necessarily have to just be the peak amplitude, just any point on your wave, and just track that as it propagates, and that will basically sketch out your wavefront. And then we have what are called rays. So a ray is just obviously a line that shows us the direction of travel for our wave. So rays are always going to be perpendicular to our wavefront. So if we have a point source here, we have a point source here that's emitting. So if you drop a pebble in a lake and you get like circular waves moving out from it like this, your rays are just perpendicular, right, to that wavefront at every point. So this is perpendicular right there, and these are all perpendicular. So then here we have plane waves, and here this represents our wavefront, the blue line, and the rays again are just perpendicular to that and go straight. Okay, so that's wavefront and rays. We're going to be talking about rays a lot, especially when we do lenses and get more into optics. We're going to be using exclusively rays. So now let's get into reflection and refraction. So when we have, let's say there's some medium here. So let's say we're going from one medium to another. So this is our other medium. And this has some index of refraction and then some other index of refraction. When our light ray comes in to our medium 1, strikes the surface at our medium 2, some of it will get what's called reflected, right? It'll be reflected off the surface, just like a mirror. And then some of it will get what's called refracted. So maybe it will sort of bend a little bit like that. So when light gets refracted, it just means that the light ray gets bent a little bit as it enters the medium. So you can see here if I just drew like, a straight line from where it was coming in, the light ray would have just gone straight like that. Instead, when it entered this medium, it got refracted and the light got bent a little bit. So we have reflected and refracted. So usually when a light ray hits any surface, both things will happen, right? Like if you're looking out a window, you can both see your reflection in the window, but you can also see outside the window. The same thing if you're looking at like a puddle of water, you can see your reflection in the water, but you can also see what's beneath the water. So most of the time at an interface, you have both reflection and refraction. However, for our problems, we're usually just going to be looking at one. So it will be obvious from the question if we're looking at the reflection part or the refraction part. And obviously how these light rays interact with the medium depends on the indices of refraction for both. So there's two different types of reflection. When we have reflection at a smooth surface, like in a mirror or like a very flat body of water, you have what's called specular reflection. So that means that all of the light rays, they come in like this, and they all get reflected at exactly the same angle, right? All of these light rays get reflected perfectly, and that's why you're able to see a perfect reflection in a mirror, because all of the light rays go into the mirror and then they're reflected exactly back, all in the same direction, so you can get a nice coherent image. Now, when we have reflection at like a rough surface, like on concrete or something, you obviously can't see your reflection in concrete, and part of the reason is because when you have a rough surface, the reflected rays get, they get reflected in all different directions. So this is called diffuse reflection. Okay, so now let's look carefully at refraction. So remember that light always travels slower in a medium than in a vacuum, and we have the ratio of the speed of light in a vacuum to the ratio of the speed of light in the medium is called the refractive index, or the index of refraction. So we call that N. And we're going to be using that a lot in the next couple chapters. And remember also that the larger the index of refraction, the slower the speed of light in the material. So the larger N you have, the more your light gets slowed down in that material. Okay, so now when we want to talk about reflection and refraction, so let me draw what we had just a second ago. So we have some, material here. And we have N1 on one side and some other material, N2 on the other side. Now when our light ray comes in, so we have some light ray coming in here, and it gets reflected here. When we talk about the angle of reflection or refraction, we're always measuring from the normal to the surface. So we have a normal line, so a perpendicular line coming out of the surface here, right? So it's coming, the light ray is coming into this surface, and we're measuring the angle from the normal. So we always talk about this angle. So this is our what's called angle of incidence, and then this is our angle of reflection. So usually the angle of incidence will be given by theta A, and then the angle of reflection is given by theta sub r. So very important to remember that they're both measured from the normal. Okay, a lot of people make the mistake and measure it from here. That's like a very easy mistake to make, because that's kind of like the obvious angle that you see, but it's measured from the normal, so that's very important. And the same thing goes for when we talk about refraction. So when we're looking at how our light ray bends once it's in the material, again, you have a normal there. And let's say our light bends like that. You're still looking, this angle is the angle of refraction there. I'll use a capital R for that. Okay, so very important to remember, that's the normal that you're measuring from. That's like the number one mistake people make when they're doing reflection or refraction problems, that they just don't get their angle right. So that's like the number one thing to remember about this, is just make sure that you're always using the normal to measure from when you're talking about the angles, or when you're doing a problem and they mention an angle to you. Okay, so now we have the law of reflection. So the law of reflection just says that the angle of incidence and the angle of reflection are always going to be the same. And that kind of makes sense, right? Because if we have, if this was a mirror, and you have a light ray that comes in, it's going to be reflected at exactly the same angle that it came in at. It doesn't really make sense that it would, for some reason, be reflected, down here, or be reflected over there. It makes sense that it just bounces directly off the mirror and makes the exact same angle as the angle of incidence. So that's what our law of reflection is. It just says that any angle, our angle of incidence and our angle of reflection. So we have there, that's our normal. We have our angle of incidence and our angle of reflection, and those are the same. And again, obviously measured from the normal. Okay, so then that's our law of reflection. Then we have the law of refraction. So the law of refraction is a little bit more difficult. Obviously, we've got some signs. This is also known as Snell's law. So the Snell's law is given by, the index of refraction of the first medium times the sine of the angle of the sine of the angle of incidence, and then that's equal to the index of refraction of the second medium times the sine of the angle of refraction. So if we have a medium here, we have some angle, some light ray coming in like this. It gets refracted. This is our normal. We have the angle of incidence here, which is theta A. Our theta B is right here. And then we have N1 and N2 on either side of the mirror. So anytime we have a light ray coming into a medium, it will obey this law if it gets refracted. Okay, so just a few things to remember about Snell's law. So for Snell's law, if we have our second medium has a higher index of refraction than the first, the light ray will bend towards the normal. So here you could see you have your incident ray here. This material has a lower index of refraction than this one, which means that light travels slower in your second medium. The light ray will bend towards the normal. Now, if your second material has a smaller index of refraction, so it travels faster in that medium, it will bend away from the normal. So if your ray now comes in exactly along the perpendicular, so it makes a 0-degree angle with the perpendicular line to the material here, it will not get refracted at all. It will just go straight through the material, along that straight line. Okay, so this also explains why when you're looking at something in water, the shape of it seems to change, or it looks to be somewhere that it's not. Because if you're, let's say we're looking at this ruler here. We have this ruler just obviously in reality goes straight through the water like this. Water has a higher index of refraction than air. So if you're looking at this ruler in water, anything in water, the light rays get bent when they meet that water-air interface. So it looks to you, your brain thinks that the object is just directly where your eyes see the light rays coming from, right? So you think that the end of the ruler is right here because your brain's not taking into account, the fact that there's an index of refraction for water. Even though the end of the ruler is really down here, it looks to you like it's there. So it looks like the ruler bends because this happens along every point of the ruler. Okay, so now we're going to look at what happens to the wavelength and frequency when a light wave enters a medium. So we said already that we know, remember we have the velocity is lambda times the frequency, and we already said we obviously know that the speed of light is going to change in a medium, right? So this is going to change when it enters a medium. And we said a couple lectures ago that the frequency does not change, and the wavelength does change when a light wave enters a medium. Now the reason that is and that the frequency can't change is, let's assume that we had some surface here. So let's say we have some light wave going into our medium right here, and let's say this is going in at 1 hertz. So 1 cycle per second, 1 wavelength per second, is being created by our source up here, a star or something. Now when it goes into this medium, what happens if the frequency changed? If the frequency changed, so let's say now it's at, 2 hertz, once it enters that material, how would that physically be possible for the number of cycles per second to change in the medium? Because up here, we have 1 cycle per second, which means this star is outputting 1 wavelength per second. But now in this medium, we're going to see 2 cycles per second. That doesn't make any sense because that means at our boundary, something would have had to create an extra cycle per second, right? We would have had to create an extra wavelength somewhere on our medium. And that doesn't really make sense because the thing out here is creating the cycles per second, not the medium, right? So that's why the frequency has to stay the same, is because the thing outputting the waves is not changing. It's not affected by what medium you're looking through. It's putting out a set number of cycles per second regardless of what medium you're looking at it through. So that's why the frequency can't change, and only the velocity and the wavelength will change when you go into a medium. So since we know now that the wavelength will change, it changes according to the index of refraction. So the lambda naught here is the wavelength in a vacuum, and then it will decrease by a factor of n, a factor of the refractive index, once it goes into another medium. And since the index of refraction is greater than 1, the wavelength will always decrease once it goes into a medium, because this down here is always greater than 1. All right, so now let's do an example with all this. So here we have a thick glass bowl filled with water. The index of refraction of the glass is 1.52. We have an incident ray in this water, making an angle of 60 degrees with the normal. Find the directions of the reflected and refracted rays. Okay, so the reflected is easy, right? So the reflected ray, I'll call that theta reflected, is going to be exactly the same as the incident ray, right? So this is 60, so we know that the reflected ray is also going to be at 60. So this is just 60 degrees. So now the refracted, okay, I'll call this theta B, and then we'll call this theta R. Okay, so theta B is our refracted angle, so we're going to use Snell's law here. So we're going to have NA sine theta A is equal to NB sine theta B. Our NA is the index of refraction of water, which is 1.33. So we're going to be using that a lot, so you'll probably end up just memorizing the index of refraction of water. So that's 1.33 for water. And then we have sine of 60 is equal to the index of refraction of glass times sine theta B. So let's divide both sides by 1.52. So we'll get sine theta B is equal to 1.33 times sine of 60 over 1.52. And now we're going to have to take the inverse sine of both sides. So we'll get theta B is equal to sine inverse of 1.33 sine 60 over 1.52. And this gives us 49.3 degrees. So we have 49.3 degrees here. So that means this angle here from the normal is 49.3. And this makes sense because we said when a light ray goes from an index of from a lower to a higher index of refraction here, we said that it will bend towards the normal, which is what ended up happening here, right? It bent towards the normal. This angle is smaller than this angle. All right, now let's do another example here, but this time with the wavelength. So we have the wavelength of red light from a helium neon laser is 633 nanometers in air, but 474 nanometers in some liquid solution. We want to know the index of refraction of the solution and the speed and frequency of light in it. So let's do the wavelength first. So that's easy because we know that for the wavelength, it just obeys this equation, right? The wavelength in a vacuum divided by the index of refraction is the wavelength in the medium. So we have this lambda and this lambda, so we just solve for n. So we have n is equal to lambda naught over lambda. So lambda naught is in, so here they have air. The index of refraction of air is almost exactly 1. It's like 1.003. So you can basically just treat air as like a vacuum. So we'll just say 6.33 nanometers is like in a vacuum. And then we have 474 nanometers. So the nanometers cancel, and this comes out to 1.34 for our index of refraction. And now that's essentially water, because water we said was 1.33, so this is basically a water solution. Okay, now let's look at we want the speed, okay, so let's find the speed of light in this solution. So we know that the index of refraction, we said is the ratio of the speed of light in a vacuum to the speed of light in some medium. So to find the velocity, we just solve for v there. So we have 3 times 10 to the 8 divided by the index of refraction, which was 1.34. And we get that the speed here is 2.25 times 10 to the 8 meters per second. So it's slowed down a little bit, not a whole lot. But okay, and then we want to find the frequency. So let's find the frequency using the velocity and the wavelength inside this medium. So remember, the velocity is lambda times f, so that means f is the velocity over the wavelength. So our frequency inside this solution is 2.25 times 10 to the 8 divided by 474 nanometers, because that's the wavelength inside the material. So 474 times 10 to the negative 9 is nanometers. And this comes out to 4.74 times 10 to the 14 hertz. And now let's just check that our frequency did not change, and let's compare this to the frequency in a vacuum. So let's say that we'll call this f prime, and our frequency in a vacuum would be the speed of light, so we would have 3 times 10 to the 8 divided by the wavelength in a vacuum, which was 6.33 times 10 to the negative 9. And if you do this, you get the same answer. You'll get that the frequency is 4.74 times 10 to the 14 hertz, so our frequency doesn't change as we expected. Okay, now let's do one more example. So here we have two mirrors that are perpendicular to each other. So I'm going to draw the diagram. So we have two mirrors that are perpendicular to each other like this. A ray comes in, let's say like that. Okay, and then this angle, this ray, so let's put a normal here, is being reflected at some angle, we'll call that theta 1. Okay, so we've got some angle theta 1 here. And we want to know what is the final angle it's going to be reflected at. Well, we know when it hits the first mirror, it's going to be reflected at the exact same angle that it came in at, right? So it's going to be reflected like this to the second mirror. So it's going to be going that way, and we know we're going to have theta 1 here again, right? Because it's the angle of incidence and the angle of reflection is the same. So now we can draw another normal here. Now you can kind of guess what these angles are going to be, but let's just check to make sure. So we have a right angle there. We know that this angle is going to be 90 minus theta 1, right? Because we know that this angle, this is a normal, so this entire angle here has to be 90 degrees. So if this is theta 1, this is going to be 90 minus theta 1. And then we know in a triangle, the degrees all add up to 180, right? So in a triangle, we have 180 will be this angle plus this angle plus this angle. So we'll have 180 is 90 for this right angle here. Then we're going to have plus this angle. So plus 90 minus theta 1. And then what does that leave for this angle? So then we're going to have plus some, we'll call that theta 2. So what is this angle theta 2 then? Well, we can just solve this right here. We get 180 is equal to 90 plus 90, so that is 180. And then you have minus theta 1 plus theta 2. So you can see right away that these obviously cancel, and you get theta 1 is equal to theta 2. So this angle now is just the same as theta 1. So we've got theta 1 there, so let me make that blue. So this angle here is theta 1. So now when this ray hit this mirror, it's going to be reflected again, right? So it's going to be reflected out like that. So now we can see that this angle, so again we have a right angle right here, so we have theta 1 here. This is going to be 90 minus theta 1, right? So its incoming angle to that mirror is 90 minus theta 1, which means the reflected angle is going to be 90 minus theta 1, right? And then we also know that this angle is also going to be theta 1. So now you can see here that it was actually reflected basically exactly in the opposite direction it came in at, right? because we have this parallel line here because we have this perpendicular line to the first mirror, right? So this line here is parallel to the second mirror, right? So this and this are parallel, and we have an angle of theta 1 with both of those. So it's reflected just directly in the opposite direction. It's perfectly anti-parallel because we have theta 1 here and theta 1 here, and these are two parallel lines here. Okay, so now let's move on to something that's a little bit similar to what we just did. It's called total internal reflection. So when you have light going from a medium of higher refractive index to a medium of lower refractive index, so here it's water and air, you can get what's called total internal reflection, which means that all of the light is reflected back at the interface and none of it is refracted through. So here we have some incident ray, and it goes through the interface of the water and air, and it just gets refracted out, which corresponds to, let's say this light right here. So it just gets bent a little bit and comes out, and that's fine. Then here, if it comes in at a certain angle here, it will bend so that it's exactly along the surface here, right? So that means that the angle of refraction is 90 degrees, right? So we have a 90-degree angle there compared to our normal, or you could call it 90 degrees from here, doesn't matter. This is called the critical angle. So once you get to the critical angle, if you have any angle that's bigger than that, all of the light will get reflected. So now we have here some angle, some incident angle that's larger than the critical angle, and all of the light is actually just reflected back at the surface and none of it is refracted through. So that is what happens right here. The angle is a little bit bigger here, meets the interface, and then is just reflected back at the surface. So that's called total internal reflection. Again, the critical angle is the minimum angle for which this happens, and any angle larger than that will get total internal reflection. And it's also very important to remember that the second medium has to have a lower index of refraction than the first. Your light ray has to be going from a medium with higher refractive index to a medium with lower refractive index. Otherwise, it won't work. So the way that we write this, we can write this using Snell's law. We just write that the sine of the critical angle, so if we want to find the critical angle, is equal to the second refractive index divided by the first. And the way we found that was because we said we know Snell's law is like this, and b sine theta b. And we said that the angle of refraction here, we said was 90 degrees, right? So if this is 90 degrees, sine of 90 is 1. So that just means that we have a case where sine of theta A is equal to NB times 1, which is just NB. So that's where this equation comes from. And any angle, again, larger than this theta critical will give us still total internal reflection. Okay, so one of the most common uses for total internal reflection is fiber optics. So like your internet, phone, cable, everything basically is fiber optics with that. So the way it works is you have these tiny cables which are made up of some kind of glass with a very high refractive index. Usually they use some kind of silica glass. So you have this very high refractive index here, and then you can shine light down this tube. So it basically just keeps the light wave inside this tube by having a high refractive index here, and then basically encasing it with something with a very low refractive index on the outside. So down the entire tube, you get total internal reflection, and you can transmit signals this way. So that's how fiber optics works, is they make use of this total internal reflection. Okay, now let's do a quick example with total internal reflection. So here we have, in which of the following situations is their total internal reflection? So if we have light propagating in water strikes the water-air interface at an angle of 70 degrees, well, for that one, let's find the critical angle first and then figure out if 70 degrees is larger than or smaller than the critical angle. So we have NA or we have sine theta critical is NB over NA. And we know right away that we can see that the water is a higher index of refraction than the air, so we know that that works out. We have the first medium has a higher index of refraction than the second, so that part is fine. So now let's just find the critical angle. So we have, we're going to have to take the inverse sine, so we'll have sine inverse of NB, which is air, so that will be 1 divided by 1.33 is the index of refraction of the water, and we get that theta critical is equal to 48.8 degrees. So as we can see here, 70 is obviously bigger than 48.8 degrees, so total internal reflection is possible in this case. So this is for part 1, so that's fine, that checks out. Now for part 2, let's see, we have light propagating in glass strikes the glass-water interface at an angle of 70 degrees. So now we're going to have this same, we're going to start with the same equation, but now we're going to have different indices of refraction here. So we're going to have theta critical is equal to the sine inverse of the, let's see, we have glass water. So NB is the index of refraction for water, which is 1.33. And then the first index of refraction, NA, was glass, which was 1.52. So you take the inverse sine of that, and you get that theta critical is equal to 61 degrees. So again, we can see here that 61 is obviously less than 70, so our angle of incidence was greater than the critical angle, and total internal reflection will work there. Now for part 3, we have light propagating in water strikes a water-glass interface at an angle of 70 degrees. Well, there we have our NA and NB. Water is 1.33 and glass is 1.52. So here, actually, our second index of refraction is greater than the first. So total internal reflection will not be possible here because we need the first index of refraction to be greater than the second, not the other way around. So that won't work. Okay, so now let's do one more example with total internal reflection. So here we have light incident along the normal face, so it's incident right here. We have a prism of refractive index 1.52. Find the largest value the angle alpha, so this angle down here, can have without any light refracted out of the prism at face AC. So the light comes in like this, hits this interface right here, and then we want it to be totally internally reflected and just reflected back this way, none of it to come out. So the first thing we can do with this problem is we know that we're going to be looking at a normal here, right? So let's look at this a little bit closer. So when we're talking about when this light ray strikes this interface right here, the angle of incidence will be this, right? So this is the angle of incidence. And then we also can see that this alpha here, since this line and this line are parallel, this angle and this angle will be the same. So this is also alpha right here. So we can see now that alpha plus theta will be equal to 90. So alpha plus theta will be equal to 90 degrees. And remember that the critical angle corresponds to the smallest possible angle for total internal reflection. So the critical angle is the smallest theta here, but the smallest value of theta here will correspond to the largest value of alpha here, right? Because if alpha plus theta is equal to 90, when you have theta at a minimum, alpha is going to be at a maximum there because they have to equal to 90, right? So if we find the critical angle, that will automatically correspond to the largest angle alpha, which is what the question asks for. So let's find our critical angle here. So for part A, we have if the interface, so we have glass for the prism, and then it's immersed in air. So our index of refraction out here is just 1. So that will mean we'll have sine of theta critical is equal to NB over NA, where NB is the index of refraction of air, and NA is that of glass, which is 1.52. So then we take the sine inverse of that to find the critical angle. So we'll have sine inverse of 1 over 1.52. And this gives us for a critical angle of 41.1 degrees. So now all we have to do is just have alpha is equal to 90 minus theta critical. So we just use this here and solve for alpha now that we have theta critical. And we get that alpha is equal to 48.9 degrees. And now we can do the exact same thing if this prism is immersed in water, except now here, right, so we're going to start off with the same equation, but now here our NB is that of water, not of air. So it's going to be 1.33, which is still less than the index of refraction of glass, so total internal reflection can still occur, but we're just going to have 1.33 here instead of 1.52. So for part B, we're going to have the critical angle is equal to sine inverse the index of refraction of water divided by the index of refraction of glass. And we get that the critical angle is now 61.3, so it's much bigger. And then again, we can do alpha is equal to 90 minus 61.3. And now we get that alpha is equal to 28.7 degrees. Okay, so that's this problem. So now let's just talk briefly about dispersion. So previously we were treating, when we have a light wave entering some medium, we were assuming that all of the wavelengths of light get basically bent the same amount. But that's actually not true. So typically you have, for different wavelengths of light, depending on their wavelength, they get bent differently. So for this plot here, we have the wavelength of light in a vacuum. So we go from a lower wavelength to a higher, longer wavelength up here. And you can see that in different media, the index of refraction is actually lower the higher the wavelength. And then the index of refraction is higher for the shorter wavelength colors. So the index of refraction is typically higher in different medium for like violets than it is for reds. So this is the origin of like that famous prism artwork that everyone's seen. So you have white light. White light is made up of all of the colors. So white light is red, yellow, blue, green, everything. So the white light comes in and then it gets refracted inside this prism. And then it gets refracted even more when it comes back out. And then since the red had a lower index of refraction than the blues and violets, it got refracted a little bit less. So that's why those colors get separated out. And now that I'm looking at this isn't a perfect illustration because technically the rainbow should start in here as well. Once it goes into the prism, the colors immediately start getting separated out. So it actually shouldn't be white here. It should be rainbow colored. But anyway, so that's also why diamonds are like so brilliant, because not only do they have this dispersion effect where the index of refraction of diamond is very high, it's like 2 point something. So there's a lot of dispersion going on in diamonds. So the reds and blues and violets are all separated out from each other quite easily, but also they're cut in such a way that you have total internal reflection. So you basically have you'll have a light wave that comes in here, it gets dispersed, so now all the colors are separated, and then it's also totally internally reflected between the facets, and then that's why when it comes back out at you, you see all of those colors. is due to both dispersion and total internal reflection. Okay, and this also explains how we get rainbows. So when we have rainbows, what happens is you have obviously they're usually after it rains, so there's a lot of water droplets in the air, a lot of like raindrops suspended in the air. So you have this light you have light coming in along these lines right here. So you have light coming in. Once they enter the raindrop, they get refracted inside. And again, since the different waves of light have different indices of refraction, they get refracted at different angles. Then they get reflected again at the back of the raindrop, and then they finally come out the same side that they went in. So here's this is a bunch of we have 6 rays here, which might be a little bit confusing, but this is an example with just red and violet. So with just red and violet, you have the light from the sun coming in here. You can see that they start getting refracted immediately, and then once they come back out, they're separated a little bit. So that's how rainbows happen. Here's a picture of a rainbow I took in Utah. So those are rainbows. And now let's just do one more example with dispersion. Okay, so here we have the indices of refraction for violet light and red light inside a diamond are given. It's 2.46 and 2.41. The wavelength of violet light is 400 nanometers and red light is 700 nanometers in a vacuum. We have a ray of light traveling through air and strikes the diamond surface at an angle of 53.5 degrees to the normal. We want to calculate the angular separation between the two colors of light in the refracted ray. So that means that we have, let's say this is the diamond surface here, and the ray of light comes in like this. Our red will be refracted like that, and then the violet maybe like that. So what we're looking for is what is this angle, this separation between the two colors here. So the first thing we should do is just find the angle of refraction for both colors separately. So let's do red first. So red, we know we're going to be using Snell's law. So Na, it's going through air, so it's going to be 1 times sine of 53.5 degrees. And then in diamond, the index of refraction for red light is 2.41. 2.41 times sine of theta b. And we want to solve for that angle. So we're going to have sine theta b is equal to sine of 53.5 divided by 2.41. Take the inverse of that, so let's just write that there. So we're going to have sine inverse of all of this, and that gives us 19.48. So we get 19.48 degrees. Again, this is from the normal. So this is our normal here. So for red light in here, this angle is 19.48. Okay, so now for the violet light. So let's do violet now. So for the violet light, we're going to have pretty much the exact same setup with Snell's law, except we're going to have a different index of refraction. So we still have 1 times sine of 53.3 is equal to now 2.46. We have the higher index of refraction. And then we want to solve for theta b, so we're going to have the same thing as before. Sine inverse, we're going to still have sine of 53.5. And then instead here now we have 2.46. So sine of theta b gives us 19.07 degrees. So now all we have to do is just find the difference between 19.48 and 19.07. So that will give us, so the angular separation between the two colors is just 19.48 minus 19.07. So that gives us 0.41 degrees is our answer. All right, so that's it for today. We'll finish chapter 33 next time, and I will see you guys then.